Okay.
Yes.
Okay, everybody. We're going to go ahead and get started. My name is Jennifer Brennan. I am the NASA Earth Science Data and Information Outreach Lead here at Goddard Space Flight Center. I will be your host today. So why don't we go ahead and go over just a few, little bit of housekeeping here. Welcome to the special two-day Global High Resolution Sea Surface Temperature Data Applications and Tools webinar. So we've got the webinar today, and we also have a second webinar tomorrow beginning at the same time at 2 p.m. Eastern Daylight Savings Time. And that will be focused on tools and data access and data discovery. Okay, so once you have been logged on via the audio bridge, please mute your telephones. We will take questions throughout. However, what you will do is you will use the question, there's a question and answers, a Q&A, we call them pods, but it works like a chat for each of the screens, so go ahead and type in your questions as we go forth, and at the end of the presentations, we will address all of the questions. Okay, so at the end of the presentations, we'll go ahead and answer those questions for you. Let's see, so those of you who are dialed in, there's no need to mention the audio bridge. So why don't we go ahead and get started here. I'll talk to you a little bit about the agenda. So this agenda, we're just going to focus on day one. Today we will be covering, it will start off with an overview of the GHRSST project along with an overview of select data products which are part of the GHRSST project. Michelle Girock and Jorge Bastos for the second 30 minutes of the presentation will be providing coastal, regional, and global applications examples of using those data products. We will finish with, there'll actually be a series of 4 polls just preceding the question and answer period. And those polls are designed to, help us determine what topics you may like to learn about in the future and to, improve over time the series of webinars. Okay, so we'll conclude with a question and answer period. That'll be 15 minutes long. However, for those of you who would like to stay on past the hour time slot, we will extend it an additional 15 minutes. Otherwise, you're welcome to drop off. This particular webinar, along with all future webinars, will be recorded. So after the event tomorrow has been completed, I will send out a link to all participants. Along with, that link will include the recording along with the questions and the answers from today's webinar. All right. Our first speaker today is Dr. Ed Armstrong.
Well, good morning, or good afternoon, or good evening to wherever you are. I'm Ed Armstrong, and I'm a data scientist, and I work at the Physical Oceanography Data Center here in the Jet Propulsion Laboratory. It's a NASA facility right here in beautiful Southern California. And in my presentation, I'm going to give you a brief overview of the Group for High Resolution Sea Surface Temperature project. This is an activity that I've been involved in for a very long time. And I'm going to give you kind of like an overview of the history and some of the kind of novel approaches to both data content and data packaging that GHRSST has done for the sea surface temperature community. In general, to support SST research and in a larger sense, applications research. And GHRSST currently has over 61 data sets. So I'm going to kind of wrap up with a short little exercise of data discovery that is a simple use case of how one might discover data amongst the 61 data sets. So I just want to say up front that I'm actually representing the larger GHRSST science community that I've been involved with for over a decade. And actually some of the slides I'm going to show you are really not my own, but they actually come from the GHRSST projects or various members of GHRSST. So you might ask, what is GRST? Well, you can go to that nice URL there right at the top, which is grist.org. That's the URL for our GRST project website, where you can learn many of the facets and what we do in GRST. But as a brief overview, essentially we're an international collaboration of satellite SST data producers who have agreed to produce their products in common data and metadata formats for all processing levels. That's level 2 through 3 through 4. And we strive for improved accuracy. And some of the novel things that we bring to the plate are these uncertainty estimates of the SST measurements that the data producers actually package on a pixel-by-pixel level for each one of their SST observations. We also package additional ancillary physical measurements, and the whole point here is that we want to present the user with variables and data that will help improve the SST interpretation and their use and their research. So we've been around actually for more than a decade. But we've actually been producing these data in these they're actually in common NetCDF data model formats in combination with climate forecast metadata. And we've been producing these since about 2005. And we generally have data from almost every single polar orbiting and geostationary infrared and microwave sensor at the moment. So some things about our organization, we actually have organized ourselves in this kind of shared task framework. I'll have another slide towards the end. I'll have a little more detail about that. But essentially, it's broken down into these regional producers of the satellite data, the local or institutional centers of expertise for a particular satellite data that actually produce the level 1, level 2, all the way up to perhaps even the level 3 and level 4 data sets. Secondly, data distribution, ingest, and cataloging. That's actually done right here at the JPL PODAC. So we handle all the ingest, the near real-time distribution, and metadata cataloging. And we also pass off these data and metadata to the NOAA National Oceanographic Data Center. So they're actually responsible for further data distribution and also archiving. And this is all kind of managed vis-a-vis a GRST project office that's in the UK. So this is a nice slide that shows all various levels of various different satellite sensors. Some of these are now defunct, but you probably recognize some of these, including AVHR and POSE, the GOES imager, NVSat, ATSR. There's actually a few of them missing on there. Things like VIIRS, GCOM, the MedOps series. Those are certainly additional platforms that we are currently receiving data sets on. But you get the idea that we produce data for nearly every single orbiting sensor that's flying currently. This little figure shows how GRST is building on heterogeneous observations. If you're familiar with radiometry, you know that microwave can essentially see through clouds but has a much lower resolution than the IR measurements that are blocked by cloud. That's a classical problem with IR remote sensing. And this little figure just shows the different components that are part of the GRST product suite. On the left-hand side there, we see perhaps that would represent a geostationary observation from GOES, so you're seeing lots of kind of medium resolution observations from the meander in the Gulf Stream, and in the center there would be an IR measurement. It's higher resolution, but of course some of the information is blocked by a cloud. And on the right-hand side is a much lower resolution, but it's a microwave instrument, so it actually can penetrate through clouds. And we also leverage off in situ data actually to tie our space observations back to reality in all weather conditions. And at the end of the day, GRST intends, one of the missions of GRST was to produce these level 2 data sets with the information, the ancillary uncertainty, and other ancillary components that would be suitable for these data blending operations through optimal interpolations. And these are known as the level 4 data sets. Well, going back a little bit to the history of GRST, there were some SST requirements that drove its initiation and conception, and those flowed from this ocean modeling activity that took place in the last decade called GODAE. That stands for the Global Ocean Data Assimilation Experiment. And essentially that particular activity was asking the SST community for improved SST information from satellites with the requirements of global coverage, spatial resolution of better than 10 kilometers, accuracy better than 0.5 degrees Celsius, updated every 6 hours, and of course available in near real time. So those are the requirements that drove the initial GRST data sets, and certainly we have many data sets that actually exceed those requirements, including improved spatial resolution as well as accuracy. So these GRIST data sets were originally designed to address some of the classical difficult issues that still remain in sea surface temperature observations from space, including defining SST at the sea ice edge, characterizing the diurnal variability, which is quite complex, as well as providing these uncertainty estimates to facilitate their use in ocean model data assimilation systems. Now, here we see a figure that shows an example of a temperature profile through depth. And one of the things that the GRIST community has strived on was to improve some of the accuracies and the formal characterizations of sea surface temperature. So if you're familiar with some space-based radiometry, you know that the infrared actually senses the skin SST, while, let's say, a microwave sensor, such as on AMSR, actually senses a little bit deeper than that. We call it's actually characterized as the subskin temperature, about a millimeter or so depth. And then there are other measurements at depth, at specific depth, measured by various in situ instruments. And one of the things that GRIST has strived for was this definition of the sea surface temperature foundation temperature. And this is a temperature there at the lower end there, where you see the little arrow, that's actually beneath the diurnal signature that these two particular profiles show. So the one on the right is this classical daytime temperature, and under the influence of strong diurnal warming, solar insolation, and light winds. And the one on the left, the very thin red one, is of course a nighttime temperature, classical nighttime temperature depiction, where the SST observed from space is very closely represents the SST foundation temperatures. So, of course, as you imagine, these the SST signatures are, especially in the daytime, are strongly modulated by these heat and momentum fluxes and other diffusive and advective processes. And one of the issues that the GRIST community is working on is towards an improved understanding and representation of these types of signatures, as well as trying to use space-based observations through modeling and other kinds of approaches to get at this sea surface foundation temperature. And these actually names that sea surface temperature, skin sea surface temperature, these are all actually now officially these climate forecast standards names. So they actually have been registered and are recognized as common metadata standard names for these particular sea surface temperature observations. Well, this little time series is from a buoy in the Indian Ocean, taken many years ago, but it shows some of these issues of temperature representations throughout the day under strong diurnal conditions. So what you see here is various temperature signatures at different depths at different times of the day, as measured from a moored buoy, as I mentioned, in the Indian Ocean, all the way from, say, 1 millimeter down to 5 meters there. But the idea here is that thick red line, that is a line that in our mind represents the sea surface temperature foundation temperature. And this, again, is the temperature where these diurnal signatures actually have collapsed down to the same temperature at the end of the day or well into the night as you approach the early morning dawn hours. And this is this temperature that we define as free of any diurnal warming signature. And it is a temperature that many level 4 data producers strive to reduce, often by using only nighttime satellite observations, or rather blending only nighttime satellite observations, or perhaps through a diurnal model, applying that to daytime observations and correcting them to the foundation temperature. Well, this little figure now shows some of the components that are packaged into a NetCDF L2P granule. And as I mentioned, besides the SST observations that you see on the top left, there are many, many other variables that a researcher could leverage on to improve their understanding of the SST measurements. Those include things like the SST, the data producer's estimate of the bias, or the standard deviation, that's the ST error there on the lower panel, and other types of ancillary measurements such as wind speed. That would be certainly important for doing diurnal warming studies to understand when the wind is either low or strong, as well as looking at things like solar insolation, that's the SSI, or aerosol optical depth, that's the AOD, right there at the right. So all of these ancillary measurements, including these uncertainty estimates, are all packaged together with the SST and a NetCDF granule, all commensurate in the same time and space grid, so the researcher can very easily leverage these other measurements as they're doing, using the SST data for their research or applications. Well, the GRIST strategy, this particular slide is just kind of an overview of the GRIST production strategy. Again, we're going all the way from these level 1 P radiance observations, adding these quality SSESs with these are the essentially the uncertainty measurements. The single sensor error statistics is what that acronym stands for. And they are all packaged together in the L2P granules with the SST observations. And then, you know, this packaging essentially makes them suitable then for further use in creating either level 3 or even higher, you know, blending them, merging them through optimal interpolation or other types of mathematical techniques to these level 4 data sets. And of course, the level 4 data sets are these, you know, gap-free, generally one map, global map per day if it's a global data set. That are produced from the native L2P data. And you know, these level 4 products, they contain a variety of different sensors that the provider might blend in them. Some of them perhaps might be a combination of IR plus microwave, or some other ones might add actual geostationary observations. So there's a kind of a good variety of level 4 approaches that various data providers have taken when using the GRIST L2P observations. Well, this slide shows some of the shared, the framework for the shared task sharing framework that GRIST has designed itself around. It's kind of a complex diagram with certainly lots of little icons. At the top there, we see what we are known as the Regional Data Assembly Centers, the RDACs, and these are the native producers of either L2P, L3, or L4 data. And certainly you might recognize some of those logos. You know, there's production coming from the NCDC, from JAXA, from ABOM in Australia. So all over the world, our partners are producing these level 2, level 3, level 4 GRIST compliant, NetCDF compliant data sets. And they then pass those on to what's known as the Global Data Assembly Center, and that's just another name for the PODAC now. So as I mentioned earlier, we do all the ingest and cataloging of the data and provide a distribution access point for all these various data sets that are coming in every single day. And tomorrow you'll hear some more about the various tools and services that we provide to access and visualize and extract the data. So I won't go into that at all. But then, as I mentioned, the third component of this particular shared production framework is the NOAA Long-Term Stewardship and Reanalysis Facility. And that is just another name for the NOAA NODC, the National Oceanographic Data Center. And after 30 days, we pass the data to them, and they ingest it, archive it, so they're the long-term archive for this particular activity, as well as they serve as another distribution point, and they have also a nice suite of tools and data discovery type interfaces that a user can leverage. And if you want to read some more about this, there was a nice little paper that kind of laid out the entire GRIST project that was published in BANS by Donlan et al. In 2007, as well as there's some URLs there in the lower right to provide nice little access conduits to the particular activities. So one of them points to us here at the PODAC, another one points to the NODC, and then the lower one is actually the URL again of the GRIST project website. So I'm going to go into a little data discovery exercise. I'm almost done right here. And what you're seeing now is a little screen grab from actually the PODAC portal, and it shows how our user is actually accessing the entire collection of the group for high-resolution SST data sets, all 61 of them. And through that clicking there, it actually exposes all of them, but through a collection of facets, then you'll be able to kind of drill down through through further facets to kind of refine your search. And I'll give you a little bit of example of that. So if I can move on to my application now, please. I'll share my screen here. And I'll choose my application. All right, so hopefully you see a browser now that has the PODAC front end to the PODAC website right there. As I mentioned, there's these various different facets here now you can actually go through to actually discover PODAC data, but we have them ranked by parameter or platform. But I'm going to choose collections. So a collection is essentially what we consider kind of a grouping of similar data sets. And we group all the GRIST data sets into one collection. So I'm going to click on one right here. And now this is going to expose all 61 GRIST data sets for me. And of course, there's many pages to this, and it's very complicated. So, it's essentially kind of a challenging, it's a challenge actually to find perhaps the data that you want from this collection of 61 data sets. But if you look over here to the left, there's actually a nice set of these facets that we've organized: grid resolution, there's time and space, there's processing level, there's actually platform. So if you know some particulars of actually the data you might want to look at, it's actually quite easy to find. So for example, say you want a level 2 data set. You want it to be very high resolution, so you want something on the order of a kilometer resolution, and you want it to be global. So let's try to find that data. So if we go back up to processing level here, we can click on level 2 swath. And if you see this little number over here, you'll recognize there's actually 29 level 2 data sets. There are actually quite a number of level 2 data sets in the GRIST catalog. Let's click on level 2, and now this exposes all the various different level 2 data sets that we have in the GRIST catalog. So we see MODIS in there. There's some stuff from AVHRR. So as I said, we're interested in high resolution. So let's over here click 1 kilometer. Now we're further refining the search to the 1 kilometer data set. And finally, let's say that we're only interested in global ones. So we click down here and we click global, and now we expose all the global data sets. And now we're down to a collection of 6. So we have ACSR, we have some AVHR, and we have MODIS. So that is one example of data discovery. And I think I'll wrap up with that. So thanks a lot for your attention, and we'll move on to the next speaker.
Okay. Our next speaker is Michelle Gierach.
So, hello everybody. My name, as Jennifer mentioned, is Michelle Gierach. I'm an ocean scientist here at NASA's Jet Propulsion Laboratory.
Please mute your speakers.
But I'm also
Please mute your
project
telephones.
scientist for the Physical Oceanography Data Center, also here at JPL. So, since Ed sort of gave you an overview of GRIST, and there's 61 GRIST products, what we thought would be a good idea is to show you some applications for those of you that are not familiar with GRIST data sets and what you could do with it. So specifically what the scenario I'm looking at is more so a regional study, specifically using GRIST data sets to observe coupled ocean atmosphere phenomena known as ENSO, or El Nino Southern Oscillation, that occurs in the equatorial Pacific. So for those of you that are unfamiliar with ENSO, basically there's 3 different phases. There's the neutral phase, as you see here on the left-hand side. Then in the middle you have La Nina, and on the right-hand side you have El Nino. So basically you can think of neutral as a normal condition. So basically you get these easterly winds, so winds from basically the east blowing west, that basically causes cold subsurface waters to be upwelled in the eastern Pacific, as you can see here by the equatorial cold tongues, these cold or blue waters that it basically extends westward into the western Pacific. During La Nina, you basically get an exaggeration of those neutral or normal conditions, wherein you get enhanced easterly winds. So you're going to be getting colder water that extends westward, more so than, let's say, during the neutral conditions. And then during El Nino, it's an entirely different phenomenon. Clearly here you're getting anomalous westerly winds. So as you can see in the neutral and La Nina, you get warm waters occurring in that western equatorial Pacific. So as a result of the wind forcing, you're actually advecting that western Pacific warm waters eastward. You get this pileup of warm waters in the eastern Pacific. And associated with that, clearly I said it's a coupled ocean atmosphere phenomena. So as you can see by the clouds there, the convection is also impacted by the wind placement. So where we're getting, let's say, precipitation or drought, clearly is also impacted by El Nino and so in general. So from this scenario, basically to look at this regional case of ENSO, the needs that I felt, or I generally look at, is I need a long time record. ENSO occurs every 2 to 7 years. So to me, I needed something greater than 10 years to look at more than one event. I need gridded data, something that's gap-free, doesn't have issues with clouds, preferably global, because there is not currently a regional product for the equatorial Pacific from GRIST. There are other regional products. and a foundation temperature, as Ed mentioned, which basically is consistent across each GRIST data set, wherein you're removing that diurnal warming effect. So the two GRIST data sets that fit those scenario needs are shown there. The first one being this level 4 AVHRR. AVHRR is a sensor. It's an optimal interpolation global blended SST analysis. As you can see below, it extends from 1981 to present, and it's about 25 kilometers in spatial resolution and daily temporal resolution. The second being the GRIST level 4 multi-scale ultra-high resolution, or Miura, global foundation SST, that extends from 2002 to present, and as the name implies, it's ultra-high resolution with 1 kilometer spatial scale and daily temporal. So again, since I wanted this long time record of these two data sets, I'm really going to focus upon the first one since it has about 3 decades worth of data. So just to show you what ENSO looks like using that specific data set, that AVHRR optimal interpolation SST product, the top plot that you see here is neutral or normal conditions. The middle plot is El Nino, and the bottom plot is La Nina. So again, if you look at that neutral condition, here you're getting the easterly winds. You're getting a little cold tongue that extends westwards. During El Nino, you're getting warm SSTs across the entire equatorial Pacific, again, due to westerly winds vecting that western Pacific warm water eastward. And during La Nina, you're basically getting enhanced easterlies, so you get more of a cold tongue, or colder waters that extend further west. But using SST, again, since it's one of the longest variables that we have from satellites, there has been an emergence of a new type of El Nino that, again, was discovered using SST, and that is called the El Nino Modoki, Central Pacific El Nino, Wormhole El Nino, Dateline El Nino. It goes by multiple names. But for this case, I'm going to just call it the Central Pacific El Nino. So on the on the left-hand side, you have the classic Eastern Pacific El Nino that I discussed previously, and on the right-hand side, you have that new type of El Nino, the El Nino Modoki. So you can clearly see between the two, the main difference being the placement of the wind. In the classic Eastern Pacific El Nino, again, predominantly have those those westerly winds, whereas in the Central Pacific El Nino, you have westerly winds as well as easterly winds. However, I should note these easterly winds are much more weak than, let's say, the neutral or La Nina conditions. But given this sort of these two different wind fields coming together, you basically get the warm cool waters being confined in that Central Pacific, which is basically what you're seeing. The warm waters representing here the red and the orange. So from the GRIST data set again, the one I used previously, that AVHRR optimal interpolation SST product, we can basically see the difference between the two types of El Nino. The top being the Eastern Pacific El Nino, the bottom being the Central Pacific El Nino. So you can see the differences. In the Eastern Pacific El Nino, again, SSTs span the entire equatorial Pacific. During the Central Pacific El Nino event, it's really confined to that Central Pacific domain, where you're actually getting in the Eastern Pacific a little bit more cold waters than in the Eastern Pacific El Nino. So this is just another way of looking at these two different types of El Nino. Everything I've shown you thus far has been total SST. Now what you're seeing here is, in fact, sea surface temperature anomalies, where an anomaly is just a deviation from above or below normal, if you will. So on the left-hand side, you have the Central Pacific El Nino. On the right-hand side, the Eastern Pacific El Nino. Red here denotes temperatures above normal. Blue and green would be temperatures below normal. So again, you can just see that given the naming convention, where the warm water is going to be located. Central Pacific El Nino, the waters are warmer in the Central Pacific, vice versa for the Eastern Pacific El Nino. So scientists like myself, we need some kind of way to classify what's happening with regards to the Eastern, or to the equatorial Pacific in general. We need to have some way to classify it, and most people use sea surface temperatures to do that. So there are these things called Nino Indices. You may have heard them before. There's a Nino 4 indice, Nino 3.4, Nino 3, and Nino 1.2, as that upper plot shows you. And basically they're confined or defined for a certain longitudinal, latitudinal range, as you sort of see. So if we look at the two bottom plots of the sea surface temperature anomalies, you can basically see where you're seeing that sea surface temperature response corresponds to those Nino indices. Where you're getting the warmest waters in the December 2009 Central Pacific El Nino mainly looks like it's confined to that Nino 4 domain. Therefore, people generally use Nino 4 as the indice to represent the Central Pacific El Nino. And for the Eastern Pacific El Nino, they use Nino 3 and Nino 3.4. So once you figure out what El Nino you want to look at, or you can look at all the different Nino indices, you basically take the sea surface temperature anomalies, you average it for those domains over time, and you basically get the plot that you have over here on the right-hand side. So the y-axis is sea surface temperature anomalies in degrees Celsius. The x-axis is time. The orange represents temperatures above normal, blue temperatures below normal, and depending on some threshold that's chosen, above or below, that would classify an El Nino or La Nina. So those red boxes that you see are actually, this is the 1997-98 Eastern Pacific El Nino and the 2009 to 10 Pacific El Nino. And you can basically see for each of the Nino indices how exactly those sea surface temperature anomalies, their magnitude. Wherein for the Nino 3 region, it seems that it has the largest sea surface temperature anomaly for the 1997-98 event, whereas the Nino 4 looks to be a little bit larger for the 2009 to 10 Central Pacific. So using these kind of indices, scientists have really started to investigate, using sea surface temperature, how exactly these two types of El Nino have differed over time during the satellite records over the last 3 decades. So what you're seeing here is a study by Lee and McFadden of 2010, and they basically investigated the intensity and frequency of this new type of El Nino, again, over the last 3 decades, since 1981. So on the left-hand side, what you're seeing is the Nino 4 indices, so you can think of this as the Central Pacific region. And on the right is the Nino 3 domain, so this is the Eastern Pacific. The red bars correspond to the Eastern Pacific El Nino, the pink bars, Central Pacific El Nino, and that red dashed line is in fact the trend. So what you see looking at these two plots is that, if we look at first on the left-hand side, is that the intensity, so basically the El Nino intensity, which is here, so the amplitude, the difference in the sea surface temperature anomaly, as well as the frequency, has been increasing substantially over the last 3 decades in the Central Pacific, whereas in the Eastern Pacific, El Nino has actually decreased. So could this be indicating that we're going to be getting more Central Pacific El Ninos in the future? It could. Again, we need a longer time record, so we need to continue SST observations. But this does help us because it gives us an understanding of what exactly, if this event is to happen, what would be, let's say, the biophysical response. So we know SST. How does SST impact, let's say, ocean color and things of that sort? So these are studies that you can do, climate studies, regional studies, using SST observations. And it gives us an indication of sort of what's to come, if you will. So as I mentioned in the previous slide, basically El Nino is a coupled atmosphere-ocean phenomena, so it does impact our rainfall and evaporation cycles. So this cartoon just illustrates we need to sort of have a better understanding of how these things are changing over time using satellite records to understand how our future will be different. And with that, I'd like to say thank you. Everybody please check your phone lines and make sure that your speakers are muted.
Jorge. We're ready for you.
Oh, okay. Hi, my name is Jorge Bastos. Like Ed, I've been involved with the GRIS project for a very long time. I also work at the Physical Oceanography Distributive Active Archive Center at JPL. I'm on the project science team. I'm one of the scientists supporting salinity and sea surface temperature. One of the motivations for giving these kind of talks today is that one of the questions we're asked very frequently is, what data set do I use? What GRIS SST data set do I use for my application? And one of the messages we want to send out from this particular webinar is that the answer to that question depends on your application. So Michelle just presented an example of El Nino and La Nina, and I want to present an application of GRIS SST products to some coastal areas. Specifically, we're going to look at one test case off the coast of Peru, and but this could be applied to other areas where you have some major upwelling and major coastal dynamics. So why is this important? Why do we even care about, coastal areas? Well, first of all, some of the world's most productive fisheries actually occur along the eastern boundaries of the world's ocean. And these particular areas are actually associated with some very large gradients in sea surface temperature. Gradient basically being defined where you see a large change in the sea surface temperature over a very small distance. So these particular areas along these eastern boundaries are, again, where you'd find some of the most productive fisheries, and Peru happens to be one of the world's most productive fisheries. I'm also going to give you a brief example of one of my favorite websites that I think we all have them, but one of my favorite websites is FishTrack.com. And again, other examples of coastal areas, we're going to focus on Peru because of the time constraint issues, but, our own coast here along California, and certainly the West African coast associated with the Benguela region. Other examples where you have major upwelling and major fisheries associated with that upwelling. So FishTrack.com. Again, this is one of my favorite websites because it actually focuses on one of the major one of the major things that initiated GRIS from the very beginning was the operational use of SST data. And it's very interesting, FishTrack.com actually uses several NASA data sets. FishTrack.com uses several NASA data sets, not just SST. It actually uses altimetry. Why? Because sea level is actually changes in sea level also associated with eddies along these major coastal areas, and these eddies, especially along the front, are associated with also major fisheries. And they also ocean color, and I think that speaks for itself in terms of why that's important in terms of understanding the productivity and fisheries along coastal areas. And in fact, FishTrack.com actually uses one of the operational SST products that is produced at JPL, the G1 SST product, which is a very high resolution 1 kilometer product that's actually produced in near real time. We're going to actually focus again on two areas. The left-hand panel is zooming in the Pacific. Again, you see the the African, you see the African coast. The right-hand panel is focusing in also where you see Peru. And you also see the blue color. In both cases, you see the areas associated with cold water, blue color associated with the major coastal upwelling. If you zoom in again, and actually this is interesting, again, plug in a little bit of the functionality of FishTrack.com. They actually allow you to zoom in different areas and actually look at the SST. Again, off the Peruvian coast, you see this blue, almost blue river-like stream of cold temperatures going up the coast of Peru, again associated with the upwelling. Same thing off of Africa, but it's associated more with the Benguela current and the region of cold water coming up from the southern part of Africa that goes from south to north. So the question becomes, what, if I want to study these areas, what GRIS data sets am I going to actually use? And the first thing that pops to mind is, well, these are coastal areas. The upwelling can be associated with very small scale dynamics. The gradients that we see, the changes in sea surface temperature can actually occur over very, very small distances. So if we happen to decide on, GRIS products that actually have some fairly high resolution, we actually compared several in a test case. Actually, this work was just also recently published, if anybody's interested in remote sensing of the environment. We focused in on comparing several GRIS data sets, the Miura, which Michelle was alluding to, the 1 kilometer SST data set, like a remote sensing system, which is gridded at 9 kilometers, and also our ocean, which again is gridded at 1 kilometer. That's not one of the ones we compare, but again, I just wanted to mention that because it's in a near real-time mode, which can be used by FishTrack.com. Other data sets that we are actually comparing to the NCDC, which is at a 1/4 degree gridded, Ostia, which is at 5 kilometers, remote sensing system 9 kilometers. And again, the question is, are we going to see differences in these data sets in terms of the dynamics that we can actually see with them in some of these coastal areas? And we're going to use a very simple strategy to define and compare some upwelling scales that we actually see off the coast of Peru. I don't have the time to go into detail how each one of these are all level 4 products, as Ed was mentioning. So these are no gaps. So these products have used level 2P data to actually create level 4 products that don't have any gaps associated with missing data because of clouds or other issues. So if you look at the mean, again, this is the mean SST gradients for 2009 for 4 different data sets. The left-hand panel, the left upper hand panel is from NCDC. The right upper hand panel is from remote sensing system. The lower left-hand panel is from Ostia, and the right-hand panel, lower right-hand panel is from Miura. And one of the things that immediately pops out, we don't know whether these are, the data is at this point, without doing any comparisons, we can't say whether what we're seeing is real or not, but definitely the Miura data set that's gridded at 1 kilometer is showing higher values of mean SST gradients off the coast of Peru. If we look at the standard deviation, again, you see some similar structures, and again, in Miura, you see definitely some finer scale features associated with the standard deviation of the SST gradient off the coast of Peru. Now again, gradients are a vector, so we're actually looking at the magnitude of the SST gradients. These are not the cross-shore gradient or the along-shore gradient, but actually the amplitude squared of those two components. So it's the magnitude of the SST gradients that we're actually looking at. So if you actually look at a time series, we chose 2 different areas. One is off Pirata and one is off Pisco. Pirata is actually a little bit in the northern area of Peru, and the other one is in kind of the central area of Peru, Pisco. We just did averaging of the mean SST gradients in those 2 areas. And one of the things you'll see is consistently, this is all color-coded and consistently black. Black in this case represents Miura. And the Miura data set is showing the highest SST gradient. We also actually plotted just the values from the level 3 MODIS data and also Pathfinder just for the sake of comparison. And again, Miura is actually, representing the magnitude of the MODIS data better than the NCDC or Ostia or the remote sensing system product. The one thing that's very interesting is that all 4 products, especially off of Pisco, very clear distinctive annual cycle in SST gradients with a maximum in April of 2009. So that's very encouraging. So all 4 products are actually showing a similar the similar maximum in the late spring time frame, at least the boreal spring time frame for off the coast of Peru. Now, if you look at a very simple Hoffman diagram at about 10.5 degrees south, which again is almost in the central part of Peru, and by Hoffman diagram, simply the y-axis here is time, again, 2000 months of 2009. The x-axis is just the longitude. So you're going, as you're going to the left-hand side of the panel, you're going offshore. And the thing you'll see is, again, all four data sets, same convention. NCDC is the left-hand panel, upper left-hand panel. Remote sensing system is the upper right-hand panel. Ostia is the lower left-hand panel. Miura is the lower right-hand panel. And the one thing that you'll see is, in terms of the large-scale features, all four data sets pretty much are representing things consistently, and pretty much probably associated with the major movement of the upwelling front offshore and onshore off the coast of Peru. However, if you look at Miura, there are definitely some smaller scale structures associated with Miura that you're not seeing in the other data sets. The question then becomes, are these real or not? So we did a very simple, again, I won't go into details, just to define some upwelling scales based on the four data sets. And Miura has an upwelling scale of about 20 kilometers, a little bit higher than the other data sets, and it also has the highest magnitude for the cross-shore gradient of about minus 2.5 degrees per 100 kilometers. In this case, the sign convention just means it's getting colder as you get closer to the coast. Now, again, just to wrap things up, I wanted to show a very simple strategy. What we did is we subsampled the Miura data to the actual resolution of the other data sets. And when you do this, in fact, and you recalculate the gradients based on the subsample Miura data, it matches up very, very well with NCDC, with remote sensing system, and Ostia. So the message that comes out of this is that, in fact, Miura is not adding any noise at this pixel-to-pixel resolution. So the conclusions is, and in fact, if you do want to apply GHRSST SST data sets to coastal studies, you really want to try to use the highest resolution possible that you have confidence in. And in a test case that we used off the Peruvian coast, where upwelling leads to one of the world's most productive fisheries, the GHRSST data sets, very encouraging, also similar structures associated with gradients in sea surface temperature. We use a very simple scheme where Miura is subsampled to the resolution of these three other data sets, lower resolution, and they indicate that these larger magnitudes are probably associated with the small-scale features in Miura and the dynamics of the coastal upwelling that are not seen in the lower resolution counterparts. Thank you, and do we have the movie?
We do. We have an animation using the Miura sea surface temperature. Loading now.
I just want to show you, this is an animation of Miura, and it just shows you, this is for, I think, 2009, and you kind of, it's very interesting because you see the western boundary currents, you see the small-scale features, the mesoscale features associated with the eddies. You also see the upwelling, again, along the Peruvian coast and also the Benguela region. You see the Legatus waves very clearly defined in the tropical Pacific. So anyway, I just wanted to kind of show you. And again, Miura happens to be a combination of blended product, again, that uses AVHR, MODIS, and AMSR-E, and now actually uses WinSat also. So this is just one example, gapless data, blended product, and this is a little animation that I think shows you globally what you can do with GHRSST data sets. Thank you very much.
Well, thank you, everybody. We'll just wait for this to and actually move on to the polls unless you want it to run through, Jorge. So if you could take a couple of minutes, thank you for joining us today, to fill out the 4 polls that you see up on your screen. This would be very useful. And then from there, we will move on to our question and answer period. We did start a little bit late, and we experienced a few difficulties for this initial webinar. So for that, I apologize for any inconveniences that it caused to anybody. So know that for those questions that are multiple choice or multiple answers, though there's not a submit button once you select your, once you make your selection, those answers are submitted to us. So with the short answer question, what you'll do, you'll click on the submit button to the right of the fill in area that says type your answer here.
I don't see any submit buttons. I'm just got 4 panes on my window here.
There aren't any submit buttons for any of the questions with the exception of the poll in the lower right-hand corner that says what future topics would you like to hear about. Once you type in your response into the box, you will, to the right of that, there is a icon. There's an icon that allows you to submit that question only.
I hit return and it says the answer is submitted. So I guess all you have to do is hit return.
Yes.
Okay.
Once you select your response to the polls, your answer has been submitted.
Okay. Okay, great.
Okay.
Yeah.
Okay. It looks like everybody is has pretty much finished up with the poll. So why don't we move on to the question and answer period. I thank you again for joining us for our very first Earth Data webinar, a special 2-day series. Don't forget to join us again tomorrow if you're able, from 2 o'clock to 3 o'clock p.m. Eastern Daylight Savings Time. We will try to work out any of the issues that we had today with respect to see what we can do with respect to audio, et cetera, to make it a better experience tomorrow. Okay, so why don't we go ahead and take a look at the questions that were submitted here. For those of you who would like to drop off at this point, please feel free. Otherwise, we'd love to have you during this time period. So one of the questions came from Billy Martin, and the question is, what does CF 1.3 stand for? Is the notation SST int GRST compliant? Jorge, that question is assigned to you.
Okay, this is Ed Armstrong. I'll take those 2 questions. I didn't really give an explanation about what CF was, but that stands for Climate Forecast, and it's actually a metadata convention that we've adopted in GRST. And it helps somewhat in data discovery, but especially in the use of tools. So if your data set is NetCDF or HDF data model with CF compliant metadata, it plays very nicely in a number of visualization and other types of tools. And so that's the reason why we like CF. And 1.3 just stands for version 1.3. So regarding the CDRs, I didn't mention, but there is an area of the GRST project that is specifically concerned with CDR production and reprocessing activities. There are some data sets within GRST that perhaps can be considered CDRs. Some of the data sets that Michelle and Jorge mentioned, the ABHR_OI, that's the the NCDC produced quarter degree blended level 4 data set certainly could be. It's a very popular SST data set that has used in many climate studies, including these El Nino, La Nina studies. And another one potentially could be the Miura, although it has a much shorter time series, only going back to 2002. And there are other upcoming activities, for instance, AVHR Pathfinder, the popular climate data set from the NOAA NODC, is being repackaged into GRIST format. Actually, it already is, but it isn't widely distributed yet. And there's other activities with regards to reprocessing ATSR measurements, et cetera, et cetera. So there'll be more CDR-type GRIST data sets in the future. Hope that answers your question.
Okay, one of the other questions as we're going down here, is there a blog to collaborate on uses of the data sets? And I don't know whether or not the Physical Oceanography Data Center, if you have something like that out at PODAC. Anyone from PODAC have any feedback on that? Do you have any way for...
Hello, this is Ed Armstrong again, so I'm going to address that question regarding the forum. We do have a forum. It hasn't been very widely used yet, and we actually are in the process of reconfiguring it. I think we're going to be using some additional software interfaces, make it a little more user-friendly. But we do have big plans to use forums in the PODAC, not only for GRIST, but for a number of other missions and activities where science team members or community members have expressed desires to share information, to ask questions, and to have that all be captured in a forum. So that will be, you will be seeing improvements to our forum in the very near future. Thank you.
Okay, another question from Rachel. Does GRIST supply in situ data sets? You can also feel free to answer these questions by text, okay?
You're live.
That's actually a very good question in terms of in situ data sets. Right now, the answer is no. The only in situ data set actually that we do provide, but it's not related to GRIST, is the matchup database for Pathfinder. But again, that's not a GRIST data set. That might be changing in the future, but right now the answer is basically no.
Okay, thank you, Jorge. And it might be good to actually type the answer in as well afterward, Jorge, so that we have a record of this for the other participants and for those who are registered and did not dial in. Okay, there's another question here, an interesting topic. I'm relatively new to this area and I'm interested in looking at change in temperature in the bays along the Texas coast. Would you recommend Miura for this? Jorge, would you like to address that question?
Who had asked the question?
Melissa Rohal, is that correct?
Oh, I'm really new.
That's correct. I'm a PhD student.
Yeah. I think, yeah, you were here for the coast of Texas. Yes.
Yeah.
Okay.
Yes, absolutely. I wouldn't limit myself just to Miura. Again, you might want to start out with Miura, and then, what I always recommend is start out with a data set that makes the most sense, but then compare it with something else to validate. And again, you might want to compare it just like we did in this test case off of Peru. You might want to compare it with Reynolds to see, but I would definitely start out with Miura just because of the higher resolution. And by the way, I really recommend, if coming back for Tamal, because some of these data sets, the tools and services we have are very nice for accessing these data sets, especially Miura, which is high volume. So I would really recommend, especially, since you're looking at a specific area, some of these tools and services like Threads could be very beneficial for that. I hope that answers your question.
So that actually gets to, you just touched upon another question by Jorge Velez. I hope I'm pronouncing that pretty close. And his question is, he's understanding that he can actually access the data sets for free, but is interested in knowing what kind of software can be used to view the data sets, and is the viewer software also free? The short answer to that is, and yes, there's free software. I suspect a lot of that will be covered tomorrow if you're able to attend, but would anyone from PODAC like to further address this question?
Yeah, I'll address this question. This is Ed Armstrong again. So as I mentioned, with the packaging our data sets in this NetCDF, CF compliant data and metadata model really helps a lot with being able to, with a perspective of interoperability and playing nicely with tools. And all of our data sets, play nicely in tools such as Panoply, in Live Access Server that you'll see tomorrow, and other types of standalone tools like NCView. And those two tools that I just rattled off for you are all free. And we actually have also software readers that we call. These are like standalone programs that users can implement to actually read the data into memory on their local computers. And we have software readers written in a number of different languages, including IDL and MATLAB, and actually R and Python now as well. So there's a number of different software possibilities for using and visualizing the data. I also wanted to respond to the previous question with regards to in situ data and how GRIST is interacting with the in situ community. Actually, there are some GRIST members that are actually heavily involved in packaging in situ observations for quality control of GRIST data sets, and there's a nice tool built by the NOAA folks called SQUAM, and they actually have packaged various in situ observations in these very nice HDF compliant files that are very easy to use. So I would encourage you, I don't have a URL off the top of my head, but if you just do a Google search on NOAA SQUAM, that's SQUAM, I believe. It's the interface, a quality control interface that NOAA has designed for satellite observations, including GRIST data sets. As well as there's another component in Europe. The French actually have built what's known as a match-up database that actually contains in situ observations, and I don't have the URL for that off the top of my head either. You can send me an email offline, but they've essentially packaged a database where, commensurate with satellite observations, they've packaged, the nearest in situ observations that are available from things like, drifting buoys, moored buoys, and other types of in situ observations from ships. Thank you.
Hey, hi, this is Prasenjit. I have a short comment on that one regarding the in situ data. I actually just posted a link to the quality control in situ data. If you could see that, it's called IQUAM. Can you guys see that?
Sorry about that, Prasanjit. I thought it was SQUAM, but yeah, it's IQUAM. I'm sorry about that.
Yes, QUAM is the quality monitor, but IQUAM serves the in situ data.
Thanks for that clarification.
Thank you.
Sure, no problem.
Okay, Jorge, another question that came in by Spencer Farrar. GRIST product is a consolidation of different types of sensors. Hence, within the data set, does it state or flag the sea surface temperature as infrared only, microwave only, or a combination of sensors? Jorge, did you hear the question?
Yes, yeah. The level 4 products are actually a combination both of microwave and infrared. For example, that's a great question. I didn't have time to go into in details. I know Ed didn't either, or Michelle, but just to give you an example, the Reynolds data is actually a combination of AVHR. There's one product, a combination of AVHR, which is infrared, ancillary, which is microwave, and then in situ data. the other data sets are combinations. For example, Miura is a combination of AVHR MODIS, which is infrared, and AMSR-E, which is microwave. One reason that the Reynolds data set is used so widely in climate, for example, is because all of the biases are removed with respect to the in situ data. So all of these things are, it's just an example of how, again, understanding the data and your application becomes so important before you decide to move forward with using this particular data set, GHRSST data set, or that data set. And that's one of the questions, it's good to ask yourself, what are the data sets that actually went into this level 4 product?
Okay, thank you, Jorge. There's another question by David Weissman. The microwave satellite sensors are not always in time proximity, SSMI versus AMSR. So how is the microwave data product derived? I assigned that to Ed, but anyone is welcome to answer the question.
So with regards to your question, I assume you're referring as how the, again, how the level 4 blending process might work. And different data producers, take different tacks to assembling their level 4 data sets. Of course, many of the satellites that go into level 4 data sets, all of them are not time coincident unless they're exactly in the same orbit, say, or on the same platform, say, the MODIS and AMSR instrument on the Aqua platform. But, the approach from different data providers varies. Some of the data providers, perhaps take all the available data and might implement some kind of diurnal warming implement a diurnal warming model to perhaps correct some of the daytime measurements to a foundation temperatures. Other data producers, such as the Miura data set, only blend in nighttime observations. So some of these issues of coincident time are not as much a problem.
Okay. Does that mean when we access these data sets, there's enough auxiliary information to know about these special features that you just mentioned about daytime, nighttime, and interpolations and things like that?
That's a very good question and a very good point. And unfortunately, that type of specific information is not available yet in a GHRSST granule. That is probably a problem that we should work on to actually, perhaps on a pixel level, to present some information to the user of exactly what information went into making that pixel, that blended level 4 pixel. But really, you probably have to go back to the individual data provider or his research papers where he describes his methodology to kind of attack that problem. But you bring up a really good point. We've thought about that, and I think in our next evolution of the level 4 data sets.
Will we be able to know who the provider is? Actually, remote sensing systems is always easy to access. There's no question about that. But I saw some of the other sources which I'm not that familiar with, so it's maybe a naive question, but like OSTIA or PODAC folks, would they have answers similar to that? Or they can lead us to the answers? Jorge,
if we don't have the answers here at the PODAC, where we distribute these level 4 data sets, we can certainly put you as the user in touch with the technical expert at the data production facility to answer some of those questions.
That should work fine. Thank you very much.
Thank you.
I'm looking through here, and it doesn't look as though we have additional questions that have not been answered either verbally or with text on the question and answer log. So any other questions from anybody who's still dialed in? I'll take that as a no. Again, we thank you very much for joining us for the first Earthdata webinar ever that we've hosted. Webinar for the tools, data discovery and data access tools that Rosanna will be giving tomorrow, again at 2 p.m. Eastern Daylight Saving. Well, one of the pieces of information I will share with all of you is I will have an additional contact list for all of the speakers who are present, along with perhaps a couple of other links for resources, for example, the Physical Oceanography Data Center website, so that that'll be part of your recorded package that will be sent out to you. So thank you very much for joining. I sure appreciate it.